My name is Arash Mahdavi and I'll be your host today. The webinar agenda. So we are going to cover 4 models and this is how this is laid out. The first model is a basic introduction to the material handling library and all different agent types, base markups, and some logic blocks. And I suggest you just watch the entire webinar for now and you can replicate them later. This first example specifically, just watch it. It's basically just some introduction to the blocks. The second example, building operation, it's going to use majority of the space markups and logic blocks, so you learn how to build conveyor systems. Example 3 is focused on path-guided transporters and also overhead crane. And example 4 talks about levels, which is a new functionality added to the AnyLogic. And you can also see how you can use free space transporters and jeep cranes. In this specific example, it's going to be a tower crane. And at the end, we'll have a Q&A session that I will answer all the questions that we couldn't answer during the webinar. Some prerequisites for this. My assumption is you're already familiar with the AnyLogic user interface and you know process modeling library, so we didn't start from the beginning. If you are not familiar with those two concepts, for the basics of the user interface, you can look into help, just look into these sections and learn how to work with the AnyLogic graphical interface. And if you are new to process modeling library, a good start would be these 2 tutorials, Bank Office and Job Shop in the help. And there are some other resources like the books that you can find under the AnyLogic web page under resources. We are going to share the entire video recording of the webinar and also all the models that I'm going to show during the webinar. So you don't need to worry about that. If you need to replicate these models later, you will have all the necessary resources that you need for that kind of replication. The model that I'm showing, again, just to be clear, the model that I'm showing in example 1 is just for introduction to the blocks and building and the space markups. You don't need to build it, just watch that. Models 2 to 4 are the ones that I intended you to build again on your own time and learn from. And the model building in this webinar is going to be a little bit faster. I try to put as much as information that I can in this 1 hour mark. Still, it's going to be a little bit over 1 hour, so it's going to be 65 to 67 minutes. Yeah, when you have time after the webinar, when you get access to the video recording, that would be hopefully this week, you can build these models on your own pace, and it might take more than what you see in the webinar, but you have access to the source code and ALP files. So if you need to go back and look into the actual model and see how things are laid out there, you have access to everything you need. As I mentioned, we will try to answer all the questions during the webinar. If there are some questions that need more explanation, I will do that in the Q&A section at the end of the webinar. And if we didn't have enough time to answer some of your questions, I guarantee you that we will answer every single one of them in the follow-up material that comes with the video recording and the models. At the end of this webinar, you get a short survey, and it will be super helpful for us to get your feedback for our future webinars and to tailor it towards what you need. As I said, I'll come back at the end of the webinar for the Q&A section, but for now, we're going to watch those 4 examples that were in the agenda. So I'll come back and thank you for your attention.
AnyLogic's material handling library lets you simulate and analyze end-to-end processes on factory floors and storage facilities. In a nutshell, material handling library lets you simulate movement of goods with conveyors, transporters, lift, and cranes. With its out-of-the-box functionalities, you can evaluate warehouse or factory layout alternatives, simulate processes in warehouse or factories, including the conveyor systems, cranes, and AGV fleets. Analyze the performances of different production line designs and test their capacity for production ramp-up. You can also allocate resources such as staff and equipment to avoid unforeseen bottlenecks and provide simulation-based scheduling. You can also predict system behavior and analyze cost in case of breakdowns. Material handling library also lets you simulate crane operations and maintenance. It also lets you manage AGV fleets and simulate their interaction with conveyors, manufacturing machines, and operators. In this webinar, I'll showcase how you can use the out-of-the-box capabilities of Material Handling Library to simulate conveyor systems, transporters, and cranes. I'll also show the use cases of levels, which is a newly added functionality that lets you to easily create multi-level models. Let's start by focusing on conveyor systems. I start by creating a new model and I name it Basic Conveyor. Looking at this library's palette, we can see that there are three main sections: agent types, space markup, and logic or process blocks. There is also a second block section that is a selection of process modeling library blocks that are duplicated here for easy access. Similar to other vertical libraries, Material Handling Library lets you to build more specialized agent types that have many built-in functionalities on top of what you get from using the generic agent type. For now, let's focus on the material item type. You can see that, similar to other libraries, you can drag and drop a new material item type from the palette into the graphical editor and follow the steps on the wizard to set its animation and add custom parameters. Since the agents that are built from a material item type occupy physical space in the model, AnyLogic needs to know the dimensions to be able to check the validity of the model logic. The size of each material item is defined by three dimensions: length, width, height, and by default they are set to 1 meter. When you set these dimensions, AnyLogic adds a 2D outline of the bounding box that represents the physical 3D boundary in its graphical editor. To see this, make sure that you are inside the item's agent type, not the main agent type. Here I'm adding a rectangle as the 2D animation of this item. In this 2D outline, the edge that aligns with the x-axis is length, and the edge that aligns with the y-axis is the width. You cannot see the height since it is perpendicular to the view area. Back to main, I start a flowchart by adding a source. In most cases, the block that builds the items and adds them to the flowchart is source. It also has a setting that lets you change or override the default dimensions of the item that you've set in its agent type. You can also change the dimension of an item programmatically at model runtime with function calls. Aside from its dimension, another attribute of a material item is its orientation. Looking from above and in a 2D plane view, each item has 4 sides: front, rear, left, and right. The front side is parallel to the y-axis and is on the right side. In other words, the front side of the item is oriented toward the positive direction of x-axis. By default, items enter the first conveyor with their front side forward. The orientation of an item can change by function calls or a transfer table, which we will cover later in the webinar. Going back to the Material Handling Library palette, you can see that we have access to several space markup elements. Let's start with the conveyor. The conveyor markup element represents a single continuous conveyor. Geometrically, this is a multi-segment path with straight and arc segments. You can use the same techniques used for drawing paths to draw conveyor paths. We can use the scale object to scale our physical space. To learn how to use scale when you have a background layout that has a reference length, please search for Defining Animation Scale on AnyLogic Help. Conveyor has many adjustable properties, including maximum speed, initial speed, acceleration, deceleration, and the gap between items. It also has a type: belt, roller, and fixed cell conveyor. Before we can test different types of conveyors, we need to review a fundamental logic block of material handling library, that is Convey. The Convey block lets you move agents or items along the conveyor network. Two main settings in the properties of the Convey block are Convey From and Convey To, which set the start location and destination of the items being moved by the conveyor network. In the Convey From drop-down menu, you have three options: Conveyor, Position on Conveyor, and Current Position. When an item is added to a conveyor network for the first time, it has to be put on the conveyor. Aside from conveying the item to its destination, the Convey block can also add an item to the conveyor network. In this case, Convey From should be set to the entrance conveyor. Now we add a simple flowchart using a source and convey block to represent the movement of items by the conveyor. The source block generates items that move along a conveyor with a specific arrival rate. Note that in the advanced section, the option force pushing is changed to be inactive. Due to the convey block not having a built-in queue, if the beginning of the conveyor line is already occupied, new agents will not be able to enter. If force pushing is enabled when this happens, it will cause a logic error and the model will throw an error. Disabling the force pushing option allows you to choose what happens to agents that can't exit, either to store waiting agents in the source or delete them. You can also create a buffer queue and place it between the source and convey blocks. Okay, let's add a convey block after the source and draw a conveyor. In the properties of the convey block, we set the Convey From and Convey To the same conveyor space markup. The difference is that in Convey From, the zero offset is from the beginning of the conveyor, but in target conveyor, the offset is from its end. I know the start and the end of a conveyor from its direction, which is based on how I drew the conveyor and is indicated by the arrow on top of the conveyor. If you need to reverse this, you can right-click on a conveyor and select Change Direction. To complete the flowchart, I add a sync block at the end. You might have noticed that the layout or physical structure of the model is separated from the process logic. This is a fundamental principle used for process-centric models in AnyLogic, including in process modeling library, fluid, pedestrian, rail, and road traffic libraries. In general, the model building can be separated into three main tasks: drawing the space markups, building the model logic with flowcharts, and connecting the flowcharts with the related space markups. Let's change the default agent with a custom material item. To do that, you have to drag and drop the material item from the palette. Now I will add a rectangle as the item's animation and add a red line to highlight its front side. I assign this material item to the new agent field of the source. You can see that the items enter the model with the front aligned with the conveyor direction. Before we can test different conveyor types, we should add a position on conveyor space markup near the end of the conveyor and set it to be initially blocked. Position on conveyor represents a certain point on a conveyor, and we can add multiple position on conveyor elements on a single path. This element can be used to set a target location for items that are conveyed with convey block. It can also be used for custom locations on the conveyor where an item is placed or picked from the conveyor. You can also use it to simulate photo eyes, scanners, or other devices that perform some instant actions when the item's leading edge enters or its trailing edge exits the location of the space markup. You can also model all types of stops and escapement devices by calling the block and unblock functions for any of the location on conveyor markup elements. I decrease the arrival rate to add more gaps between the incoming items. Now we are ready to test the behavior of 3 different types of conveyors when items reach a blocked position. Basically put, we can say that the conveyor type defines the accumulation capability. The first and default type is roller. It is an accumulating type of a conveyor. What this means is that if an agent is stopped on it, the roller will keep on rolling, bringing all the preceding material items to the stop one, thus forming a line of agents. However, the agents in front of the stop point will be able to keep moving forward. The second type is belt, which is a non-accumulating type of a conveyor. What this means is that if an agent is stopped, the whole conveyor stops. This prevents agents behind the stop one from colliding into one another. The third type is fixed cell. Like the belt type, it is also not an accumulating type, and if an agent is stopped, the whole conveyor stops. It is made up of a succession of cells of a specialized size set by the cell size parameter. As you can see, this library has many other space markup elements like transfer tables, turntables, station, and turn stations. We are going to use them in the next example, but for now let's focus on the conveyor spur. This element is used to define a junction between a branch conveyor and the main conveyor. This kind of junction does not change the orientation of items that pass through them. One conveyor spur can only connect a single conveyor to the main conveyor, and unlike other space markup elements, adding conveyor spur does not divide the main conveyor into multiple independent conveyors. To add a conveyor spur, you have 2 options. 1. Connect 2 conveyors at any desired angle. The conveyor spur will be automatically created at the junction point. Or the second option would be to drag the conveyor spur element from the space markup section of the material handling library to the side of the main conveyor and then connect the branch to it. If the items are moved from the main conveyor to a branch, the movement can be easily simulated. However, if the branch merges into the main conveyor, then the transfer of materials is automatically calculated so that it does not affect the normal operation of the main conveyor. If necessary, the material items on the branch conveyor will be delayed until the flows of both conveyors can be safely merged. If you click on a conveyor element, you'll find a priority section in its properties window. Changing the priorities of a main conveyor that only has one merging branch does not do anything, and the main conveyor is treated as a higher priority. However, if 2 branch conveyors with incoming flows are connected to the left and to the right side of the main conveyor at roughly the same offset via a conveyor spur element, AnyLogic will compare priority values specified for both conveyors. The material items incoming from the conveyor with the higher priority value will get preference. Back to our model, we can now add more conveyors with the help of Conveyor Spare. One important benefit of material handling library is that the convey block moves material items through the conveyor network with automatic routing. Basically, one convey block can direct agents or items through the entire conveyor network. In its properties, all you need to do is set the initial and final conveyor, as well as any specific conveyors to include or exclude in the routing. By avoiding or including some conveyors, you can change the default routing behavior, which is to take the shortest path. I'm demonstrating a scenario here. Now that we went through some elementary capabilities of this library for building conveyor systems, we are ready to build a simple model that uses more logic blocks and other types of space markups. This model is about a made-up conveyor system that moves parts to a station, where 3 parts are welded together. After the welding, some percent of the items will need inspection for quality assurance. Finally, the welded items that failed their inspection are separated from the rest. Let's start by creating a new model that I call welding operation, and I'll keep the default model time, which is in seconds. I'll start drawing a conveyor by double-clicking on the conveyor space markup to activate the drawing mode. To end the drawing, you can double-click. I'll keep the default properties of the conveyor. Now I'm adding a second conveyor that intersects with the main one and would be a second entrance for items into the main conveyor. AnyLogic automatically adds a conveyor spare markup in the junction. I renamed this new branch as Conveyor South Entrance. Now I move the network a little bit up to make room for the logic blocks. If you need logic blocks like source, you can both find it in process modeling library itself, or for the most used ones, they are also available in material handling library. We will start a flowchart by adding a source block and a subsequent select output that specifies the percentage of items that enter from each entrance. We also need 2 conveyor enter blocks to put the items on the conveyors. All items, irrespective of their entrance, will be conveyed to the end of the main conveyor. We'll also need a sync block to end the flowchart. Now I change the names of the 2 conveyor enter blocks to Conveyor North Enter and Conveyor South Enter. I also changed the name of the convey block to Convey to End. Now we need to update the properties of logic blocks, starting with source. The arrival rate is 3 per minute. Force pushing should be unchecked to destroy any agent that can't exit the block. I renamed the select output block to select enter and set it to 0.7 probability, meaning that 70% of incoming items enter from the north conveyor and the rest from the south conveyor. For both conveyor enter blocks, I select the associated conveyor space markup. Items will enter the beginning of these conveyors with 0 offset. All items should be conveyed to the end of the main conveyor. Since we already put the item on the conveyor system with convey enter blocks, here in the conveyor from menu, we should select current position. Target conveyor is the end of the main conveyor with 0 offset. In this example, I separated the task of putting the item on the conveyor and conveying them. I could have used two conveyor blocks, but the current design is a little bit more explicit since it shows that we have two entrances and all items are conveyed in a uniform way. Now let's change the generic agent type generated by the source with a custom one that has a customized animation. Drag and drop the material item type into the graphical editor, select None for its animation, and press Finish. I keep the default dimensions and just add a rectangle to be the representing animation of incoming items. Going back to source, I select the newly added type, and if I run the model, we can see the animation. To distinguish between the items that enter the model from each entrance, we can add a code snippet to change the color when items exit the Select Enter block. I'll set the field color of item entering from the main conveyor to blue and the ones that enter from the south conveyor to purple. Now we can run the model and see its effect. Now we can add a station to the main conveyor that simulates the welding process. Here we weld three incoming items together into one. I set the processing time to 20 seconds and quantity to 3. Once all three items are inside the station, the 20-second processing time starts. Once done, the items will continue along the path to the end of main conveyor. As you can see, without needing to be explicitly told, the conveyor block automatically moves the items through the station on the conveyor. We want to use two welders as resources for the welding process, and we can do that by assigning resources to the station. For doing so, I first add a resource pool and rename it to welders. We have two welders, and to customize their animation, I build a new resource agent type and select the 3D animation from the road transport section. I increase the scale of the animation to 200% for better visibility. Now we need to add a home location for the welders. I can do this by adding a rectangular node with two attractors. Now I'll assign it by adding this newly added node to the home location of welders. We are now ready to add the welders to the station, and as you see, we need both welders to finish the welding process. By adding resources, we can see the utilization of those resources. If desired, I could add more granular control like shifts and brakes or other custom tasks to the resource pool. So far, 3 welded items leave the station as 3 separate items. To batch the welded items into one, I first need to separate the conveying into 2 steps, first to the station and then to the end of the main conveyor. If you run the model, it will not show any changes from before, since the same convey process is just happening with 2 blocks. To batch the welded items into one, I use a batch block with a batch size of 3. For the welded items, I create a new material item type that has a length of 3 meters. Going back to the batch block, new batch should be set to the newly created welded material item. Since we are substituting the 3 welded items with a new item that comes out of the batch, items should leave the conveyor on exit and be removed from the space. Please note that by default, when the item reaches the end of the conveyor block, it remains on the conveyor network and physically takes space on the conveyor. To put the newly built welded item that comes out of the batch block onto the conveyor, I start by adding a position on conveyor space markup on the main conveyor right after the welding station. Now I need a conveyor enter block to put the welded item on this position markup. Similar to before, the welded item will be conveyed to the end of main conveyor. It is possible that some of the welded items will be flagged for inspection. When this happens, we have one engineer who is in charge of inspecting the flagged welded items for quality. I'm building a home location for that engineer now. I also add a resource pool that creates the engineer and is assigned a custom resource type with a customized animation. Similar to the welders, I'll increase the animation scale to 200%. Home location of the single engineer is at the newly added node close to the welding station. Now it's time to add the inspection process right after the welded item is put on the conveyor and before the convey to end block. I add a select output block with a probability of 0.5 to say that 50% of the welded items need inspection. Those that need inspection will go to a service block, and eventually all welded items are conveyed to the end of the main conveyor as it was before. To be able to visually see the items that need inspection, I change their fill color to orange. The service block will use the engineer for the inspection, and it's set to take 20 seconds. Engineer has to move to the station before it can start the inspection. That is why the sent sees resource should be checked. To be able to know if a welded item passed the inspection or not, I add a passed variable inside the welded material item. I set it to be true by default because some items automatically pass the quality control and do not need inspection at all. For 50% of items that need inspection, we will know if they pass the inspection or not after the inspection service. Therefore, in the onExit field, I write some code that assigns a false value to the passed variable if the inspected item did not pass the inspection. Otherwise, the passed variable will keep its default value, which was true. As you can see, the chance of not passing the inspection is 50%. I also changed the field color of the item that was set to orange, either to red if the item failed the inspection or back to green-yellow if it passed it. During the runtime, 50% of items leave the station immediately after the welding process, but for the other half that need inspection, they turn orange and wait for the engineer to inspect them. These inspected items will turn red or green depending on their inspection result. Let's now imagine the conveyor south entrance conveyor has a weak motor that fails very often, and the engineer that inspects the welded items is also in charge of its repairs. To do this, I'll showcase how we can programmatically control a conveyor. I'll model this by first adding a path from the engineer home to the south conveyor. I add an oval that we'll use as an indicator for the current state of the conveyor's motor. We'll model the motor of the conveyor as a resource so that we can use the resource pool's built-in failure mechanism. I assign two distributions to the initial time and time to the next failure fields. We'll change the repair type in the next step. The usage statistics are set to counted as busy. Busy in this case means the percentage of time that the motor was in repair. The utilization of the motor would be 1 minus this value. Okay, now to connect this resource pool with the conveyor space markup, we write some code on its onFailure and onRepair fields. I also changed the field color of the indicator oval to visually see the state of the motor. Going back to the repair type field of the motor, I want to model the repair explicitly with a process that uses the engineer. Therefore, I need to change the repair type to send to flowchart. Now I build the repair flowchart by using a resource task start, service, and a resource task end blocks. The service conveyor block will use the same engineer that also is in charge of the inspection. Repair is set to take 4 minutes to complete. The option for send cease resources should be checked so that the engineer moves to the node near the conveyor before it can start repairing the conveyor's motor. Now we go back to the conveyor motor and assign the repair process to it. I also changed the default color of the indicator oval to green-yellow. Now we can run the model and see that when the motor fails, the engineer moves toward the south entrance conveyor, repairs it, and then goes back to its home location. Since we have one engineer that is shared between two tasks, he will become the bottleneck when he is needed both for inspection and repair of the conveyor motor. AnyLogic lets you to assign priority to tasks or even let tasks with higher priorities preempt the other ones. You can experiment with these settings to see the effect of different allocation policies. The last thing that I want to add to this model is to separate the welded items that failed the inspection from the rest. We'll also add some extra steps for the past items to go through. Let's start by adding a transfer table at the end of the main conveyor. Material items that are passing through a transfer table keep their current orientation in space. Therefore, we need to increase the width of the conveyor after the transfer table. I'll also add a turntable just before the transfer table to separate the failed items. Agents that are passing through this will turn to keep their orientation on the conveyor. Sometimes when building the network, it is helpful to disconnect and reconnect the conveyors to the turntable so it can properly adjust its internal orientations. Both the transfer table and turntable markup elements represent the actual conveyor equipment and have many adjustable properties. I kept all the defaults, but you can experiment with them. When a welded object that has acceptable quality reaches this conveyor, I also have it go through a turn station to rotate it one full turn as part of a final automated inspection. The target conveyor of the convey to end block is still set to the end of the original main conveyor, but now we have two new conveyor sections at the end, which are renamed to conveyor south end and conveyor north end. Going back to the convey to end block, we can change the target conveyor field to dynamically evaluating by clicking on the equal sign. In this field, I will dynamically assign the target conveyor. If the welded item past variable is true, it is assigned to conveyor north end, otherwise to conveyor south end. Now, by running the model, we can see the complete welding operation. We use the majority of space markups and logic blocks of the material handling library that are related to conveyor systems. In the next two examples, we switch our focus to transporters and cranes. In this example, we are going to use path-guided transporters and overhead cranes. This is a 3D visualization of the finished model. As you can see, some car engines are delivered to a location underneath an overhead crane. There are 3 AGVs that are sitting at their home location at the model initialization and are capable of moving along a looped path that has one stop point below the overhead crane and one in front of a conveyor. Upon arrival of a car engine, an available AGV is called to a node that is along the path near the overhead crane. On arrival, the crane puts the engine on the AGV, which then delivers the engine to the conveyor, and either heads back to pick another engine or returns home if there is no other engines to deliver. Let's start by creating a new model that I name car engine transport and keep its model time units to seconds. Next is to draw the looped path with path space markup. You can double click on the path markup to enable the drawing mode and then keep clicking to draw all the sections. As you can see, I did not draw the curved edges directly. Instead, I drew 4 straight segments that I'll modify to curved lines. Alternatively, AnyLogic lets you draw curved sections while in the drawing mode by holding down the left mouse button as you are placing the path's next turning point. To change the edges to curves, right-click on the path and select Edit using guiding lines. 2 new handles will be added to each path section that lets you add or change the curvature of a section. Now we need to add a rectangular node with 10 attractors that will be the arrival location of the car engines. Then I'll add a node point here, which will be the AGV's stop location under the overhead crane. We also need another rectangular node with 3 attractors for the home location of the 3 AGVs. You could also change the default orientation of the attractors if you want. I also need to connect this rectangular node to the circular path, which results in AnyLogic automatically adding a point node. Okay, now I add the conveyor that will convey the car engines to their final destination in the model. And finally, we need to add the overhead crane space markup. We need to rotate it first and then adjust its size. Overhead crane can pick up, drop off material items directly from or to a path, a conveyor, and a railway track. As you can see, overhead crane has many adjustable properties. We'll keep the defaults, but make a few changes at the end. One important caveat is that adding point nodes separates the path into several sections, and we have to make sure they are all correctly connected after the breakup. As you can see here, we have 2 sections that are not connected properly to create a continuous path. Therefore, I need to move these sections and reconnect it. Now we have 2 continuous sections that are also connected with the 2 nodes. Next step is to build a transporter fleet, customize their animation, and put them at their home location. This fleet is path guided and has a capacity of 3. To customize the transporter animation, drag and drop a transporter type to the graphical editor. Then for its 3D animation, choose the automated guided vehicle from the warehouses and container terminals section. Inside the new transporter agent type, click on the animation and increase its scale to 125%. Also change the length of this agent type to 1.5 meters to match the animation. Now we can go back to the transporter fleet block and assign the AGV type to the new transporter field. For the home locations of the AGVs, select this rectangular node with the 3 attractors. Now if I run the model, I can see the AGVs at their home location. Now I'll start building the process flowchart with the logic blocks. First, I need a source. The arrivals are defined by inter-arrival time, that is 30 seconds. The first arrival occurs at model start, and we have limited number of arrivals that is set to 9. To customize the agent animation, I'm building a new agent type and assigning a car engine 3D animation to it. This time I did not use any specific agent type from material handling library because I am not going to use any specialized functionality. I also need to set the location of arrival, which will be this rectangular node. The next logic block would be a seize transporter that will seize a transporter and move it to the loading point node close to the overhead crane. The fleet is set to the AGVs and destination to this node. At this point, the engine is put on the AGV, and now I want to move the AGV with the engine to another point node on the network. If loading and unloading of transporters could be modeled with a simple delay and the transporter doesn't make intermediate stops on the way to the target, we could use the embedded settings for seize and release in the move by transporter block. When more complex loading and unloading processes play an important role, it is better to separate the steps by explicitly using the seize transporter and release transporter blocks. Since I'm using the more explicit approach in this example, I separated the seize and move steps. By default, transporters use the shortest route on the network and try to prevent collisions with other transporters. By adding a transporter control block, you can further customize the rules of navigation in the network and the routing algorithm for path-guided transporters. In this example, we are going to use the default behavior, so this block is not needed. The beginning of the conveyor is the destination of the engine and the attached seize transporter. As I mentioned, I separated the seize and move because of the loading step between them, but I'm going to keep the embedded release mechanism of move by transporter. With the default release behavior, AGVs return to home if they do not have any other engine to transport. And finally, I'm adding a sink to finish the flowchart. There are two important settings in the seize transporter block, or the move by transporter, if you use its internal seize. The first is customized transport choice. This setting allows you to set your own AGV selection policy in the dynamic field. Here you can specify a Boolean expression that will be checked to find a specific transporter that may perform the operation. If none of the currently available transporters satisfy the specified condition, the block will wait for the first transporter that matches the condition to become available. The second option is dispatching policy, which specifies how the block chooses a transporter to perform the agent operation. If the customized transporter choice option is selected, the transporter will be chosen from the subset returned by the algorithm based on the transporter choice condition parameter. In this example, I did not change the default, but you can experiment with those options. Okay, let's run the model and observe its current behavior. Since we have not added the crane logic yet, I expect the engine to be put on the AGVs immediately. Also, we did not set any logic block for the movement on the conveyor. Therefore, engines will leave the model as soon as they are put on the conveyor. To be able to better see the animation, let's add a 3D window and increase its size to match our default frame size. I also add a camera and assign it to the 3D window. To have the camera at a desirable angle, I have to first run the model, navigate to the window 3D view and find my desired angle. I then right-click and copy the camera location to the clipboard. Back in the development environment, I click on the camera and paste the coordinates. Now, in future runs, the camera will remember my preferred angle. Now that we have a good 3D view of the operation, I can see that the engines are not correctly positioned on top of the AGVs. We can fix that by setting the position of the engine in relation to the AGV's center point with the set cargo position function. I put this function on the startup code of the AGV agent type. Doing this sets the location of cargo at initialization to 0.3 meters above the AGV's center. Now if I run the model, I should see that the engines are correctly placed on top of the AGVs. At this point, we are ready to add the Move by Crane logic block in between Cease Transporter and Move by Transporter. In its settings, I associate the overhead crane space markup with it and set the destination of the moved engines to the same node in front of the overhead crane where the seized AGV is waiting to be loaded. There are more settings for the crane, but for now I keep the defaults. Finally, I add a convey block at the end before the sync block to convey the delivered engines from their current position on the conveyor to the end. Now we can watch the entire operation with the crane and conveyor. As you can see, the guiding rails of the crane are on the AGV's path. If you want, you can go back to the crane space markup and change it to a breech crane. One other setting I'll change is component movement mode, which I'll set to concurrent to see the differences. Running the model again, you can see the difference in the crane animation and its movements. For the last model in this webinar, we are going to use levels, jeep cranes, and free space transporters. This model is about a 3-story building that has completed floors and exterior walls. To be able to distribute heavy material between the floors, a tower crane must first move the material from the ground level to the roof of the building. Then, 4 forklifts will distribute these materials between the floors. Let's start by a new model that I will name Multi-Level Delivery. In every new model, there is one level which is created automatically and is named level. All existing levels can be accessed in the projects view under the presentation group. When you select a level here, its properties will become available in the properties view. I'll change the name of default level to control level, which could be used later for building custom user interfaces that are separated from the space markups of each level. Now I'll add 3 more levels for each of the 3 floors. Each has an absolute Z coordinate in pixels and follows the scale object defined in the current agent type. In this model, level 1, 2, and 3 have Z levels of 0, 60, and 100 pixels, which corresponds to 0, 6, and 12 meters. Now, with level 1 activated, I'll start by drawing the exterior walls. I also changed the Z height to 10 pixels or 1 meter so that the interior is visible. I also add a rectangular shape that represents the floor. The Z height of this rectangle should be 0 and its fill color is transparent so that we can see through it. Now I add a rectangular node in front of this building which represents a depot of the materials that need to be lifted by the crane. I assign 10 attractors to this rectangular node. Now it's time to add the jib crane space markup. I visually resize its jib length and initial jib angle, which you can alternatively set in the properties window. I also increased all three speed-related settings of the crane. I also changed the appearance of the crane by selecting a cat head tower crane type. And I will set crane height to 25 meters so that it's able to clear the third floor. Jib cranes can also have a block zone that we are not using in this example. You should keep in mind that in order to use the move by crane block, an agent and its destination must be within the working area of a crane. In floors 1 and 2, we have 3 rectangular nodes that represent the final destination of materials being distributed by the forklifts. Here I'm adding 3 rectangular nodes in floor 1. Similar to the previous example, I'm adding a 3D window to see the 3D animation of the model. I also add a camera to set a fixed view angle. To be able to see the model in 3D view every time the model starts, I first need to add a view area item that covers the 3D window element. Here I rename it to View Area 3D. Now I write this code in the onStartup field of main that automatically navigates the view to the 3D window every time we start the model. To set the desired camera settings is similar to the previous example. We can run the model, find a desirable angle, and copy-paste its coordinates to the camera object. Now the model always starts in 3D view and at a good angle. Now I'm copy-pasting the wall, the rectangle that represents the floor, and the 3 rectangular nodes from floor 1 to floor 2. Since I have level 2 activated, elements in level 1 are grayed out. I also changed the fill color of the rectangle to differentiate it from level 1. I'll do the same copy pasting of all elements from level 2 to level 3. I delete the 3 rectangular nodes since materials will not be distributed on level 3. Instead, I need 4 new rectangular nodes that represents the home location of our 4 forklifts. I also add a 5th rectangular node that specifies the destination of objects that are moved by the crane. If we run the model, we can see all 3 levels and the rectangular nodes that we were placed on each one. To let the forklifts travel between the floors, I'll add a lift space markup starting on level 3 that will represent a construction elevator. Transporters with free space navigation use level gates or lifts to move between levels. In this webinar, we are only dealing with lifts. I resized the lift element to have a width and depth of 4 meters. For travel time calculations, every floor of the lift system must have the floor elevation properties coincide with the physical position. To simulate the lift, we place a lift element on each level. To connect these elements together, one of them is used as the main landing. The lift element defined as the main landing is where all parameters of the entire elevator are specified. In this example, I chose the lift element on level 3 to be the main landing. I also decreased the default lifting speed to 0.4 meters per second. Now I copy the lift element to level 2 and set its elevation to 6 meters. I also have to uncheck the main landing option. To associate this left element to the main landing on level 3, I choose that element in the refers to main landing field. Similarly, I copy-paste the lift element from level 2 to 1 and modify its floor elevation. Running the model, you should be able to see the lift element in 3D view. As you have seen, all space markup elements, shapes, controls, and charts belong to a certain level. In contrast, The scale element, logic blocks, and code-related elements like variables and collections belong to the agent type and are not tied to any specific level. To start building the logic, I'll build a transporter fleet for the forklifts with free space navigation type. The capacity should be 4. For home location, I have to select the 4 rectangular nodes that are in level 3. If your current active level is not level 3 and you want to visually pick the nodes, select level 3 first and then come back to the properties of the transporter fleet block. To customize the transporters, we need to build a new transporter type from the material handling library palette. I'll name it forklift and choose forklift truck for its 3D animation. Back in the transporter fleet object, I'll assign this newly built type to the new transporter field, and I reduce the maximum speed for the forklifts to 0.3 meters per second. When we run the model, we can see the forklifts at their home locations. As I mentioned, for the logical blocks, it does not matter in which level you are. Let's add a source and set its arrivals to calls of inject function. To set the location of arrival visually, I go to level 1 and with the help of element chooser, select this rectangular node. Since we want to have 10 items already in the rectangular node when the model starts, I'm injecting 10 agents by typing this code in the onStartup field of main. This means as part of the model initialization, 10 items will be already on ground floor ready to be moved to the roof. I did not change the default agent type in source, but you can add a new type to customize the animation of incoming agents. Since all 10 items enter the model at the beginning and the crane would not be able to move them all right away, we'll need a queue block right after source that let the incoming agents wait for the crane to move them. Next is the move by crane block. In the crane field, I select the crane space markup. And for the destination, I first activate level 3 from the levels menu and select this node for the destination of moved items. I also change the safe height to 20 meters. This means that items are lifted by the crane to this height so that it's clear of any obstacle that is below it in the real environment. Lastly, we need a move by transporter block that uses the forklifts to distribute the materials between the floors. However, we know that the final destination of the object could be any of the 3 rectangular nodes in level 1 or in level 2. To bundle all these rectangular nodes into a collection, I first activate level 1, select the 3 nodes in this level, right-click and select Create Collection. To add the remaining 3 rectangular nodes that are in level 2, first I activate level 2. But as you can see, although I'm in level 2, I still cannot visually select the nodes. This is because the rectangle shape that represents the floor is on a layer above the rectangular nodes. To fix this, I select the rectangle and send it to the back. Now these nodes are selectable. Going back to my collection, I add these 3 nodes to the collection. Now I can go back to the Move by Transporter block and change its node field to a dynamically evaluated one by clicking on the equal sign. With this code, I'm randomly selecting one of the rectangular nodes in level 1 or 2 that is inside the collection. As you can see in this example, I'm using the embedded seize and release mechanism of the Move by Transporter block. Therefore, I have to choose the fleet in this block. Finally, I need a sync block to end the flowchart. Now we are ready to run the model and see the entire operation. As you know, free space transporters automatically detect their surroundings and avoid any obstacles using the most efficient route to reach the destination point. Therefore, without making any change to the flowchart and logic blocks, you can change the physical layout and the transporters will still find their way to their destinations. I also add a density map to level 3 to see the heat map of forklifts as they move on the roof. Now when we run the model, you can see that the forklifts avoid the newly added obstacles. If I go to the 2D view, I can see the heat map of the movements that are happening on level 3. I hope these models were useful as an introduction to some of the functionalities that you have access to through this library. Now we can start the Q&A section to go over some of your questions.
So I hope you enjoyed the webinar. I'm going to go through some of the questions and answer them. And as I mentioned, if there are some questions that you asked at the end of the webinar that are not in this list, we are going to answer them in the follow-up material. So one question that was asked a lot was, what are some resources that we can use after this webinar? I already had this slide for you that has it's four blog posts by Anastasia, who is the lead developer of material handling library. So she wrote this fantastic blog posts, and you can read them and learn more about this library. It goes through the details of many different useful functionalities. And other resources that you can look into, if you go to help example models inside AnyLogic, there are some examples in the full-blown like models that you can look into, or you can go to how-to models. I suggest you to look at it first if you're new to this library. And under the material handling library section, you will find lots of interesting examples that are simpler and are more focused on a specific topic. The other resource is definitely help. And here you can find under the library reference guide, you have access to the material handling library. And also under tutorials, there are a couple of examples that you can look at. Lead acid battery is a pretty fairly extensive model that shows you how you can build a really good model with material handling library. So that would be for the first question. The second question is, how can you tell the direction of the conveyor? Let me go back to AnyLogic. So you probably have noticed that during the example 1 and 2, I showed you how you draw a conveyor. And when you draw that, by default, AnyLogic gives it a specific direction based on the way you drew it. And this is used when you are using things like convey that needs to know the direction. Like it needs to start from the beginning of the conveyor or end of the conveyor and takes things to the other side. So because of these kind of settings in some of the blocks, you need to know the direction, and that's important. If for some reason the default that came from your drawing the conveyor is not what you want, you can right click and change the direction as I showed in the example model. And this is the same thing for all types of libraries. You see the same logic for roads in road traffic library, railroads, and other libraries in AnyLogic, even path. So you can always change the default direction like this. The third question is why you did use the material item instead of agent. As far as I remember, I didn't use any of the specific capabilities of material item type that you have here. But when you're selecting a specific or a specialized agent type for a specific library, right, a pedestrian type, or material item type, or resource type, it comes with more functionalities that you can use for like advanced capabilities. For example, if you go to help and search for material item, you will find, for example, that it has more specific functions, like it tells you where it is on a conveyor, like where get the trailing edge of position and things like that, and you can change the orientation, get the orientation, things that make sense for that specific application. And the same goes for cars or pedestrians or trains. And and there was another point here, and what if I want to turn a regular agent into a material item? So sometimes you might have already built the agent, and one thing that I want to mention before that is from the agent panel, when you're using this agent wizard and you select a new agent type, here you can select the type. So depending on which library you're using and which specialized agent type you need, you can select it here. But if, let's say that I've built an agent type that is generic and I want to change it later after the fact, after I built it, you can go to its properties and change the type here as well. So you still get access to all of those specialized functionalities. And the last question is, how can I focus on viewing a specific level? Again, your best resource would be help, and I search here, and there are many examples that you can look at. We have this multi-level model in a hospital that you find in example models, and it actually there are some snippets of code that you can reuse for other models, how you can select a specific level when you have a more comprehensive model. But if you look into like the functions that comes with the levels, you can set its visibility to true or false, and that's how you turn a level on or off depending on which level you are, and you can build some form of custom navigation for your model. So I think these are the questions that I wanted to cover now, and I will look up to see if there are more questions that we couldn't answer right now, and I make sure that you get the answers in the follow-up material. So I think our time is up for today. One important thing that, again, I need to ask you is to give us some feedback. It is super important for us to have some feedback from you for future webinars. It helps us a lot. And just to be clear, again, everything that you saw in this webinar, the entire video recording, all the models, the source code, and unanswered Q&As will be sent to you in a follow-up email that hopefully will be out this week or early next week. Thank you again, and have a great rest of your week.